Hey, it's Dr. J. I'm back with some more derivative stuff. Today we're going to focus on the rules of the derivatives, or in particular, the rules of taking derivatives. This is just to create a more efficient method. Yeah, or create more efficient methods, right? We might have several different methods. A more create more efficient methods for finding derivatives. Because when we left off last time, I spent an hour and a half exhausting these techniques, probably for the last three videos, where you were probably going, God, there's got to be an easier way. I know that I was, and I know the easier way. And I can't tell you how difficult it is for me to not tell you the easier way, to find the result. And so I'm sitting here dragging you through the mud, when all the while I know that there's a much easier, softer way to produce the same result. So today is that day. I'm not going to make everything easier, and there will be a little bit of a trade off. And that's typical with mathematics. When one thing becomes easier, something else will become more difficult. But I will create some more efficiency, which will hopefully keep the time on my videos from going past an hour and a half. I'd like to keep it to about an hour, maybe an hour and 10 minutes if I can. So I should probably shut up and get right into the first set of rules. And so what these are quick ways of finding the derivative. So first thing I want to point out, and I think we already noticed this, is the derivative of a constant is zero. The derivative of a constant is zero. So if we have a constant function, we use k for constant. Some folks use c. I still use c sometimes, but in this lecture, I'm going to use k for constant. Then the f prime is zero. That's probably the easiest of all of the derivative rules. So what that means is that if we see a constant and we're taking its derivative, we don't need to run through the whole limit as, h approaches zero, or, the other different limits. It's not necessary. It gives us a very quick way of calculating the derivative of a constant. Okay. The second rule is the derivative of a constant multiplied by a function is equal to the constant, so the same constant multiplied by, sometimes I just want to say times, the derivative of the function. So these are probably the two most important rules. There's going to be more, but I just wanted, with the board space that I have here, I wanted to make sure I got the first two rules out there. I don't have room to put this one here, so let me put it here. So this will be rule number one, and then this will be rule number two. If you're writing this in your own notebook, I would probably put rule number two down here below here, but I ran out of space. Okay, so if you have a function times a constant, so y is k times f of x, then the derivative, I'm using the other notation, dy dx, is k times f prime of x. In other words, what this means is that when I have a constant in front of a function and I want to take its derivative, I can essentially ignore the constant, just put the constant out in front, and then simply take the derivative of the function. I'm also using two different notations. The dy dx, it's known as Leibniz notation, and then the f prime of x, which is Newton's notation. I don't have time in this lesson to give a history of the calculus, but there are two sort of competing viewpoints and how they went down in the text, and how we still use both of the different notations to this very day. And they're kind of the remnants of a great battle between two very smart minds, of which calculus was built on. Okay, that's my teaser to my maybe history lesson of calculus coming soon. All right. Okay, so those are the first two rules. I want to talk a little bit about notations. So when we have a function, I would say, f of x is equal to 4 or something, right? That's function notation. So in order to use this rule, let's focus on rule number 1 right now. With function notation, I would take the derivative and I would say f prime of x is equal to 0. Again, so that's just using rule number 1 here, the derivative of a constant. But there are two other notations that I'm going to use. I can use an equation. Right? It's still a function. It's just not written using function notation. It's just written as an equation. Y is equal to 4. Then I would say dy dx is equal to 0. And finally, over here in the corner here, barely have any room for it, I have what's called an expressional notation. It's also known as operator notation. Operator notation is where you don't have a variable. Well, I shouldn't say it that way. There might be a variable. You don't have variables on both sides. I guess you could say that this 4 could be a variable, so and it will be in a minute. It might be like x or possibly 4x, but so far we only have rule number 1 and rule number 2, and I want to dispense with rule number 1 so that I can take back this real estate and work on rule number 3, which is going to really give us some power. So this is an expression notation. I'm not writing it as a function. I'm not writing it as an equation. And I'm going to do what's called operator notation. So this is operator notation or expressional notation. Well, the reason why we call it an operator is because it's like you're performing an operation. Yeah, just like addition or subtraction or squaring or square rooting or multiplying. So I'm saying that this operation is being applied to this expression, and the result is equal to 0. Okay, and so this is what I call tomato. I call this tomato, and I call this tomate. It's just 3 different ways to say the same thing. And I've got 5 more ways to say it too. But for today's lesson, these are going to be the 3 different notations that we use. All right. And then sometimes we use a hybrid. Yeah. So this is a tomato. It's a half tomato, half tomato, right? I'm using a little bit of one and a little bit of the other. So sometimes we blend the 2 operations, the 2 notations together. All right, that is by far the easiest rule, the constant rule. And then rule number 2 is just an application of the constant rule. And it says the derivative of a constant multiplied by a function is equal to the constant multiplied by the derivative of the function. So using this operator notation, I could say d dx of k f of x. Right, I already erased it, so I wanted to write it back one more time, is equal to k times f prime of x. So that is rule number 2. And notice I'm using sort of a combination of these 2 different notations, the operator notation and the prime notation. And so that's not really enough for you to completely digest it. I'm going to do several more examples. So rule number 3, it's called the power rule. I'm not going to write this one out in words. Only the first 2 rules do I write out in words. And the reason why I like to write them in words is because they're so important. The first 2 rules are so important that instead of just memorizing a formula, I want you to understand the terminology, and so that when I'm talking and explaining things, it's more than just a recipe. The power rule is really just a recipe. And it says the derivative of an expression to a power, right, x to the nth power, is equal to, now you're going to love this, n, so the constant, that's not the same as k, I'll get to that in a minute, times x, and then you subtract 1 from the power. And there's a special case that we should probably memorize. N equals 1. In the case that the power is 1, the derivative would be 1 times x to the 1 minus 1, which would be 1 times x to the 0. This is the one you want to memorize, which would just be 1 times 1, which would be 1. So in other words, the derivative of just x all by itself would just be 1. You see how that kind of binds together the first 3 rules, right? You have the idea of the constant, right? Constants become 0, right? That's rule number 1. Okay. Rule number 2 says, well, if you have a constant times a function, then you ignore the constant and then you just do the derivative of the function, which we'll get to that more in a minute. The power rule says, if you have a power, x to a power, you multiply the power, that becomes your constant, times x to 1 less than the original power, right? And that's, if I was to write it all out in English, that's the way I would write it out. It would be a big paragraph, much larger than these. And then we memorize the special case, because this is the only one that's special. If x is 1, then it's just going to be 1 times 1. So all of this just ends up being 1 times 1, which is just 1. Any other number, any other power besides 1, then you just follow the recipe. Yeah, so if it was 2, well, then it would be 2 times x to the 2 minus 1. If it was 3, 3 times x to the 3 minus 1. All right, so those are the first 3 rules. I would say 1, 2, 3, memorize those first 3 rules. Those are the rules that we're going to use most often. There's going to be a lot. By the end of this lecture, I think we'll have, I don't know, 6 rules or something. I don't know, maybe 8. I haven't counted them, but I will count them along with you as we go through them. Okay, so let's go ahead and use the rules. So given the following, and I'm going to do one of each. So given a function, an equation, and an expression, so let's say f of x is negative 6x, y is negative 5, and an expression just x. So we have a function, an equation, and an expression. Use the appropriate notation. To complete the derivatives. All right. So we'll start off with the easiest one, f prime. F prime of x. Okay. So we have a constant times a function. So this is going to be negative 6 times the derivative of x, which is just 1. Maybe I'll notate that. It's the first example. The derivative of x is 1. So this is rule number 3. Yeah, the derivative of a constant times a function. So this is negative 6 times x. So you can think of the function as really just x. So then we ignore the constant, negative 6. Now, ignore is a strong word. You ignore it, but you have to keep it in the final answer. So in other words, you don't do anything to it. Yeah, you just transport it over to the final answer, don't do anything to it, and then multiply it by the derivative. And so your final answer is negative 6. Okay. How about dy dx? What's dy dx? Well, you have to use that one. That's the only one that has a y, right? So use the appropriate notation. This is the only one that has a y in it, so dy dx must be that. So the derivative of negative 5 is 0. The derivative of a constant is 0. Negative 5 is a constant, so the derivative is 0. And the last notation, called the operator notation, that would be this one. Expressional notation or operator notation. I'm taking the derivative of the expression x. The derivative of the expression x. That's the one we just did. That's that special case, which is 1. Again, the derivative of an x is just 1. Sometimes I write my 1 like this, and sometimes I write my 1 like that. I have never made up my mind as to which one I like better. So I keep them both around. All right, so that's example one. Not too shabby, huh? I put a lot of time into that because now that we've got the ball rolling, we're going to keep using these different rules. Let's do another one of these to kind of get the notation right. So given, let's do g of x let's do y equals x cubed. And let's do the expression x to the fifth. All right, so again, this is a function. This is an equation. And this is an expression. One of each. Determine the following. Derivatives. One thing you're not going to see today is the limits, yeah? Because when we have these rules for derivatives, it's like skipping the limit. It's almost like somebody else has already done the limit for you, and you can just apply the result of that. You know, you do that all the time in mathematics, right? You know, when you were, 10 years old and you multiplied, I don't know, 11 times 12, right? And you got 132, right? You probably had to do it once, right? When you were little, right? Someone probably made you actually work it all out. 11 times 12, you had to work it all out, right? Hopefully when you were, 11 or 10 or maybe even 9 years old, they didn't let you use a calculator to get the answer. God, that would be horrible for your childhood, experience in math, right? That would ruin you for life. But hopefully somebody, when you were 9 years old, made you multiply 11 times 12, right? That's kind of like what I've been kind of leading you through the mud, right? With all these previous videos that went on and on and on with all these calculations. That was like that was your training grounds, right? But once you got the result, right? 11 times 12, and you know that it's 132, which was easy to remember, right? 132. You never have to do it again. So for the rest of your life, you kind of just thought of that as a rule, right? That's essentially what we're doing here. We're saying, well, I know that I could drag this through the mud. I could do the limit as h approaches 0 of g of x plus h minus g of x all over h, and I could fill up the whole board with a whole bunch of work, and I would get the answer, and that's great. That's an experience. But what I'm telling you is you've already lived that experience. That's a lived experience now, and a shared experience that we've all kind of been through together on opposite sides of the screen. And so now we can just use the rule. Okay, this is rule number 3, the power rule. So this is going to be 4 times x to the 4 minus 1. This is the power rule. The power rule says take the power, turn it into the constant. So that becomes your it's sort of like k, but in the rule I call it n. I like to distinguish between n's and k's, although they do mean the same thing. But n is the power, which then becomes the constant. So there's your 4. And then the new power is 1 less than the old power. So it's 4x to the 3rd. Okay. All right. What else? Y prime. I haven't shown you that notation yet. That's sort of new. Instead of writing dy dx, sometimes we will simply write y prime. And so that'll be 3x to the 3 minus 1, which is 3x squared. I'm showing you the calculation step of the power rule. All of these use the power rule. In the future, we will just do the power rule in our heads because it's pretty quick, and then we will just write down the final result. All right. And then part C, I don't have a function like f or g, and I don't have an equation like y. So the only thing I have left to do is what's called the differential operator, d dx, of the expression x to the fifth. That's equal to 5x to the 5 minus 1. That's the last time I'll write that out. In the future, I will just jump right to here. 5x to the 4. Okay. I should make one note before I erase all of this. It occurred to me as I was boxing this last answer. Part A could have, let's call this part D. I'm going to do part A again, just one more time, because I already know the answer. I just want to show you one more version of this. When we have function notation, because we might see this in the future, we sort of combine C and A, and we write it like this. It's sort of a hybrid of C and A, and I will call that one D. Yeah. So D is CA hybrid. I'm taking the differential operator, d dx, of the function f of x, and it will give you exactly the same answer as A, but written out in a different notation. So just to make that absolutely clear, that sometimes we get the same result using a different set of symbols. Okay. So that is sort of an exploration into the different notations. For the next few examples, I'm going to stick with this expressional notation. I think it's the one that takes up the least amount of space. And so today's lesson is about learning the new rules and then also becoming more efficient. And in order to gain some efficiency, we are going to just stick with one of the two notations. So use the rules to find the following derivative. Find the derivatives. So you'll notice that this is very efficient use of space. So there's A. So the derivative of 4x, without doing any work, it's a constant times x, so it's just going to be 4. The derivative of x to the 6th. Power rule, 6x to the 5th. Yeah, doing the calculation in your head. What about negatives? Negative powers. Well, got to be careful with that one. Maybe I'll write this one out. -3 then becomes the constant. Then the power becomes 1 less than it used to be. So be careful with negatives. I have seen students that are very well, trained and well versed and, excellent students, and they will accidentally go -3 -1 and then do -2. And it's a very common mistake. So let's just be careful about that. And then what about fractions? What about a fraction exponent? Again, I'll probably write this one out. I will write this one out. So the fraction, the exponent becomes the constant. And then the power becomes 1 less than the original power. So 1/3 -1. Be really careful. 1/3 -1 is -2/3. If you want to see the fraction math, I'll do a little cloud down here. I'm just going to do the fractions. 1/3 -1/1. Then I'll multiply this by 3. So that's 1/3 -3/3. Then you subtract the tops, the numerators. So 1/3 -3/3 is -2, and then you keep the denominator the same, so it's -2/3. So that's how we get this new exponent of -2/3. Okay. Well, you see how efficient this is, though? You see, each question just takes 1 row. I can get a lot done in a small amount of space. In the next example, so I'm going to do a lot of these today, just kind of going through the different recipes. We're going to need to clean up our results, simplifying. So these last 2 examples are unsimplified, which is fine because the question did not tell me that. So I can leave my results unsimplified. I like to move along by simplifying the results. So I will tell you to do this if I want you to do it, so that there are no negative exponents or negative powers or fractional powers. So watch for this instruction if I ask for it. I really shouldn't have to say that much, but this is a new topic, these rules. Generally, I would just say simplify. I mean, that's kind of the underlying message behind simplify, which means make it as simple as you possibly can, which means getting rid of fractions and negative exponents. Okay, so let's do something like A this one doesn't have a fraction. So A Right, there's no negatives, there's no fractions, so far it's so good. I don't have anything to do yet. Let's go ahead and pull out the constant. Yeah. So a constant times a function is the derivative of the function times the constant. Right, so the 3 just sits out here and waits. I guess you could say ignore as well. I often say that. But be careful with the word ignore, because sometimes you ignore something and then it just goes away. This is not going to go away. So this is 3 times 2x to the 1. Yeah, so that's the derivative here, which is going to be 6x to the 1. I usually don't write the 1 power, so it's 3 times 2 x to the 1, or x to the first, which is 6x. Okay. Maybe I'll illustrate this. This derivative becomes this. Yeah. And sometimes it's more efficient to work down, but I'm saving this space for my next parts of the problem. So I'm trying to work horizontally as a space-saving measure here. All right, d dx of 5 over x. Well, this is the derivative of 5 times x to the negative 1 power. Remember that rule? Basic algebra rule. This is x to the first power, right? X to the first power. I'll put a little 1 right here. And so I want to bring it up to the top and make it a negative power. Now the rule says to write with the result with no negatives. So when I'm done, I will put it back to being positive, but temporarily I'm making it negative. So this is going to be 5 times the derivative of x to the negative 1. So the constant 5 is what I'm ignoring. It comes out in the front here. So that's going to be 5 times, now this is going to be messy here. What's the derivative of x to the negative 1? It's negative 1. Here, I don't have enough space to write it there. I'm just going to have to write it here. The board ran out of room. So the derivative of x to the negative 1 is negative 1 times x to the, I don't really need the dot. I'm going to get rid of that dot in a minute too. So negative 1 x to the negative 1 minus 1, which is 5 times negative 1 x to the negative 2. I switched from square to round parentheses. It really doesn't matter what kind of parentheses I use. I'm getting rid of all the parentheses in a minute anyway. So now it's 5 times negative 1, which is negative 5, x to the negative 2. Now I have to simplify so that there's no negatives. So that's going to be negative 5 over x squared. And that's your final answer. Our goal is efficiency, and just like my little story about being 9 years old and learning something and then never having to go through that again. that's something you might want to chalk up to experience. Personally, I wouldn't jump all the way to the answer. And I, I'm a mathematician trained and, well versed and holding many degrees. And I would jump to this step first and then simplify. So at least that gives you that one breath to sort of go, well, I have a chance to fix it if it's wrong. If you jump all the way to the final answer, then you really have no safety net, right? So I would go, personally, I would skip all of this. I mean, I would do it once or maybe twice to get a feel for it. And then I would just go from 5x to the -1. I would jump right to here, -5x to the -2. And then I would simplify the result carefully. Unfortunately, I used up a whole bunch of my board space here. So part C and D are going to have to go up here. So let's do part C. The derivative of -3 over x to the 4th. Okay. So that's going to be the derivative of -3x to the -4. That's going to be negative. Let me just go down here. I know I'm going to run out of room. I'm planning ahead. That's going to be -3. So the constant comes out in front. Times the derivative of x to the -4. So notice we only have 3 rules so far. And rule number 1 is, it is a rule, but it's really rule number 2 and rule number 3 that we're using quite frequently. All right, so I got -3 times the derivative of that. The derivative of that will be -4x to the -5. Okay, so I'm jumping. Remember, -4 when you subtract goes down to -5, and then I'm going to multiply the result. I'm going to put the answer here because I do have room. Negative times a negative is 12. And then the x goes to the bottom and becomes x to the 5th. I wanted to save room for my last part. If you wanted to put in an intermediary step, it could be -3 times -4 is 12. And then I would say 12x to the -5. I have one additional step here and then jump to the final answer. That would be fine as well. And then the last one for this one is how do we deal with square roots? Now, the 2 most common roots that we will see are square roots and cube roots. They're the ones that show up the most. So I will focus most of my attention on those 2 types. Let's start with square roots. So again, that's 8 comes out, and then the derivative of the square root. Now, this is something that not everybody gets a proper education on, depending on your experience, previous semesters, or I don't know, it could have been last semester if you had my class. But sometimes this, slips through the cracks. I have to admit that, I sometimes fail to mention this. It's not a big topic in other courses, but it does come up a lot in calculus. The square root is actually an exponent. It's 1/2, right? It barely gets touched upon towards the very end of an algebra course or sometimes a pre-calculus course when you're just finally finishing the course and you're probably tired and exhausted and not really paying attention. So square root is a 1/2 power. Similarly, a cube root will be a 1/3 power. So those are the 2 that we're going to use the most often. So it's 8 times, you don't really need the dot, but I like the dot because it tells me I'm not done yet. When I get rid of that dot, it means I'm done. And so now let's do the derivative. It's going to be 1/2. Yeah, the power is 1/2, comes out in front, becomes the constant. X to the 1/2 minus 1. So that's going to be 8 times 1/2 x to the negative 1/2. I'm not going to show the math this time. I'm going to say DIY. Do it yourself. 1/2 minus 1. Do a little scratch work. You're going to get negative 1/2. So now I've got 8 times 1/2, which is 4. Again, DIY. 8 times 1/2 is the same as 8 divided by 2, which is 4. X to the negative 1/2. You got to get rid of the negative first, right? No negatives or fractions. So get rid of the negative first. So the 1/2 goes to the bottom and becomes positive. And then finally get rid of the fraction. And that's your simplified answer. Some instructors, not me, but some instructors out there will make you go one step further. They'll make you get rid of the square root in the denominator. If you were in a beginning or an intermediate level algebra course, that's a very common instruction in beginning and intermediate algebra. I always wonder why we make people do it in beginning. I think it's just to keep you busy, make you do stuff. Because it turns out that when you get up into advanced mathematics, nobody does that anymore. And so I don't even bother making you do it. But if you've had an instructor that didn't allow you to have a square root in the denominator, it's called a rationalizing. I'm not one of those. So you can go ahead, and I just want you to get rid of the negatives and the fractions, if possible. But there might be times where it's not possible. All right. So we're making progress. It's time for some more rules. I think we've exhausted the first 3 rules. Now those 3 rules are probably the most important ones. That's why I've spent 40 minutes on them. But there's got to be more to this. So let's go ahead and add some more rules. So rule number 4. I hate that they're called rules too, by the way. We should call them properties or principles or something like that. But I mean, they're frequently referred to as derivative rules, and so I want you to hear me say it exactly the way somebody else would say it. So rule number 4, the derivative of an exponential. Which is different than a power. An exponential function is where you have a constant, let's call it, A. Yeah. An A is a constant. So notice the different variables or letters I use for constants. I use K. Usually K is like a standalone constant. I use N when it's a power, and I use A or sometimes B when it's a base. Right? And I really want you to be familiar with the different notations because that's 50% of mathematics is just knowing how to read the symbols. And sometimes we use B for base. Right? I'm consistently inconsistent. So I like B, but then sometimes B starts to look like a 6, especially when I'm writing it very quickly. And so I like A because it's very easy to tell that that's not a number, right? It's a base. Although, when I actually do an example, it will be a number. All right. So the derivative of an exponential is the same exponential times the natural log of the base, a, ln. And sometimes we omit the dot and just write it that way. I don't like there to be a gap between them, so I'm just going to put the dot. And if I really want to simplify it nicely, I'll get rid of the dot and squish them right up next to each other like that. Okay. And then rule number 5. Looking at my notes, I think we only have 5 rules, and then we'll have 2 special cases. The derivative of a logarithm so notice now I am using b for base. Yeah. On a calculator, they often, if you have a fancy calculator that does logarithms, it'll sometimes use a b for a base. But sometimes we use a. Right? A and b really mean the same thing. It's the base. This is 1 over x times the ln of b, whatever the b is. These rules are not very natural. They don't seem natural like the other rules. They're very sort of awkward, and you really have to be very careful with how you use them. All right. Now, so I would actually, the first 3 rules, you can learn them, you can recite them, you could do a bunch of examples and probably never have to look at your notes. These ones, I always kept this handy. I would write this on a little note card, or I would have it on a sheet of notebook paper and just have it out in front of me so that I was familiar with it. If I was taking a test, I would make sure that I reviewed these before the test, because they're not natural. It's funny because we call this the natural logarithm, but the rules seem so unnatural. And they each have special cases. I don't know if I have room to put them here. So let me say special case of rule 4. So again, we have d dx of a to the x is a to the x ln of a. Special case if a is e. Yeah, remember 2.71, 8281, blah, 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 that exponential number that we learned previously. All right, so if a is e, then the derivative of e to the x is e to the x ln of e, which is e to the x times 1. Yeah, because the natural log of e is just 1. And so that's just e to the x. So we'll call this a special case of rule 4. I mean, you could make it a new rule. I think when I was first learning this, it was listed, as a separate rule. It was the rule for E. But you find out later that it's actually just a special case of an existing rule. In some presentations of calculus, these 2 rules that I'm exhibiting now are saved until later, until you have more experience, because they can be a little bit daunting if you've never seen this before. I'll go easy on you. I'm going to give you the rules now, but I'm not really going to use them very much. I'm just going to kind of tease them into the subject as they become important. Then I will emphasize them. A special case of Rule 5. Again, let's write down Rule 5 one more time. Log base b of x. That would be 1 over x ln of b. All right. So special case, if b is e, then log base b of x is the natural log of x. And so the derivative of the ln of x is 1 over x times the natural log of e, which is 1 over x times 1, which is just 1 over x. In other words, this entire fraction here, the ln part disappears and you just get 1 over x as the answer. Okay, so what are we up to? Example 5. Now that we've got Rule 4 and 5, and again, you might want to have these handy. I know I do. I've got them right here because they're easy to forget. So example 5, I use the rules to find the derivatives. I don't really care if you simplify these, so I'm just going to say find the derivatives and be happy with it. So what's the derivative of 5 to the x power? Now we just had the formula on the board. I intentionally erased it. Again, if I were in the classroom and I had a much larger board, I'd probably have the rules written down along the side board here, sort of off the screen here. You're going to have your own sideboard. So just have a little sheet of paper out and be ready to follow the rules here. So this is a to the x, right? So the answer is just a to the x times ln of a. And that's it. You could omit the dot. I don't know if when you enter it in, if there is a multiplication dot, you can use a star, which is on the keyboard Shift 8. If you want the dot. You don't have to, though. You can just write them right next to each other with no dot. That's the way I would do it. When two expressions, functions, variables, numbers are written next to each other, we assume that they're being multiplied anyway. So the dot is not necessary. The derivative of e to the x. Oh, that's a special case. E to the x ln of e, e to the x times 1, which is just e to the x. I would probably just jump all the way to the answer. C. What are we up to? Oh, logs. The derivative of log base 4 of x. That's 1 over x times ln of 4. Again, you don't need to simplify this. I would probably just get rid of the dot. And there you go. And then D. That's a special case. 1 over x ln of e, which is 1 over x times 1, which is just 1 over x. And again, I would probably just jump if you recognize that it's a special case. All right, cool. Yeah, all right, good job. Moving right along. Example 6. So once you have these rules down for the rest of the semester, I'm going to spend a couple lectures on this, but for the rest of the semester, this will be the quintessential, guidebook for how to do derivatives, how to take and simplify and evaluate derivatives moving forward for the rest of this course. So there are 2 more rules. Rules 6 and 7. The derivative of the sum of 2 functions is equal to the sum of the derivatives. I always wondered whether or not this even needs to be a rule. I often wondered whether this needs to be a rule. And I wanted to say, well, no, it's so obvious that it doesn't need to be a rule. Well, it turns out it does. Okay. And I'll tell you why. It's not obvious for every operation. That's why we make it a rule. Right? If it was obvious that for every operation, right, like square rooting or squaring or multiplying or dividing, that if you had the derivative of something that was being, combined with an operation, we would just call it the obvious rule of operations and we could just have it be one rule. But it turns out that we need a separate rule for every single operation. Yeah, it kind of sucks, huh? So this is the rule for adding. Yeah, and it is obvious, but it still has to be a rule, right? Because there might be other ones that are not obvious. And so to make it very clear, we give every single operation its own rule. And finally, rule 7, the rule for subtraction. Is the same as addition. All right, so that's the end of the rules for today. We'll do a few more examples. Example 6. So again, use the rules. Find the derivatives. Simplify. And I'm just going to say simplify. In other words, no negative or fractional exponents. That's what we mean when we say simplify. All right, so what do we got? We got a 4x to the 9th plus pi to the 5th power. So that's rule number 6. So that's going to be the derivative of 4x to the 9th plus the derivative of pi to the 5th. Now I'm skipping all the steps now because we've already done it. And we're running long on time. I try to be efficient, but I excel at going on and on. 9 times 4 is 36, x to the 8th. Again, it's just a repeat of what we've already done. Now this one's tricky, yeah, pi to the fifth looks like an expression in which you would use the power rule, but it's not. Pi to the fifth is a constant. It's not a variable. It is a constant. That's rule number one. So rule number one is the derivative of a constant is 0. And so that is the answer, 36x to the 8th. That's your final answer. All right. I'm going to have to erase the rules, but I think that these rules, again, I called them obvious. I don't know how obvious they are, but if you know the rule for addition, it is the same rule for subtraction. Some folks just combine them together and call them the sum difference rules. Sum difference. Let's do a difference. 5e to the x minus log of x. So that's a difference. I'm going to write it a little smaller. So, difference. So it's going to be the derivative of 5e to the x minus the derivative of log of x, which is going to be 5 times the derivative of e to the x minus 1 over x ln. Here, I'm going to write it out one more time just because I have room. Log base 10 of x. This is called a common log, and it's invisible. So there's an invisible base 10 right here. If you don't see it, it's a 10. Yeah. Any other logarithm base, I have to tell you what it is. But with 10, I don't have to tell you. Okay, so now we can finish this off. 5 is the constant. The derivative of e to the x is just e to the x. The derivative of log is 1 over x ln of the base, which is 10. There you go. Derivative of three x to the fifth times 9x plus 2 Well, we don't have a rule for this yet. So in order to apply the 7 rules that we have, we first have to create an expression that falls into one of the categories, right? It has to be one of the rules. So we have sort of a preliminary step that we have to do. And that's to distribute so that we create something where we can use rule number 6. We have to have it be either a sum or a difference. So in this case, it's going to be a sum. And now we can apply the rule. So the derivative of 20, not 29, I wrote that wrong, it's 27. 3 times 9 is 27. Remember, there's an invisible 1 here. So when you distribute, that becomes 6. So that's going to be 27 times the derivative of x to the 6th plus 6 times the derivative of x to the 5th. So that's going to be 27 times 6x to the 5th plus 6 times 5x to the 4th. 27 times 6 is 162. Forgot my calculator, so I'm just banking that I remember my basic math. And 6 times 5 is 30, and then that'll be x to the 4th. 162 x to the 5th plus 30 x to the 4th. We're really cooking now, right? And I think it's interesting to note that, we're an hour and 10 minutes into this video, hour and 11 minutes into the video, and my goal was efficiency, right? And I hope that you see that this is actually much more efficient than doing the limits, right? What's really making this last longer is that these rules are new. So it's like, driving for the first time and having to, check every single thing, look left, look right, check your mirrors, all these things. But once you get the rules down, this will be a much more efficient process than the previous processes that we've had. Okay. One more of this. These are long examples too. I really packed a lot. These are densely packed examples. ddx of what do we got here? We got 6 times the cube root of x squared plus 4 to the x power minus 8x. Okay. This one will probably take up the whole board here. So the first thing I'm going to do is simplify this a little bit so that I can get ready to use my rules. So it is a cube root and a second power. So that is exponent of 2/3. So the power goes on top, the root goes on the bottom. So x to the 2/3. That's about it. The rest of these can all just be kept the way they are. Now we'll use our rule. It's going to be 6 times 2/3 x to the 2/3 minus 1 plus 4 to the x power ln of 4. That's the rule number, I don't know, what was it, rule number 5 or something? 4, rule number 4. We have 7 rules altogether. And then this is the first rule, or the first and second rule that we had, 8. That'll just be 8 because the derivative of x is just 1. So technically that's 8 times 1 if you really want to make it look totally clear. 6 times 2/3 is going to be 4. I'm going to leave it as a DIY to do your fraction math, right? It's 6 times 2 and 1 times 3. Yeah. So it's 12/3. Or it's 6 divided by 3 is 2. 2 times 2 is 4. No matter how you slice it. I'm also going to have it be a DIY. Do it yourself. 2/3 minus 1 is -1/3. There's not much you can do with the natural log here. If you put that into your calculator, you would get a big decimal and it would not be simple. So if we're trying to simplify this, that's as good as it gets. Then you can simplify 8 times 1 and just do 8. So the only real simplification happens in this first term. You want to send the x back down to the bottom because it's negative power, negative 1/3, and then put the root back on it. So it's cube root. And that, my friends, is as good as it gets. I'm almost out of time. The next example is what I call bread and butter. Example 7, bread and butter. Why do I call it bread and butter? Because it goes right back to the basics that we have learned at the beginning of this semester. Does that look like bread and butter? In other words, it's simple, polynomial. It's really what this course is built on. I mean, I do a lot of fancy, excursions and into these, I dive into these deeper pools of mathematical knowledge. But I mean, bread and butter, basic math, right? And again, in calculus, this is basic, right? This is what we consider a basic math expression. Find f prime of x. We're going to do a lot of these, right? Not necessarily today, but as we move through the course, this is going to be your daily bread here. All right? And watch why the rules have been invented. All right, we have a difference, we have a sum, we have another sum, we have a difference, right? So we're applying the sum and the difference rule repeatedly, right? I'm not going to write that all out. I'm just going to say it. We are applying the sum and difference rule, right? We have a constant, so we're going to apply the constant rule. We have an x times a constant, so we're going to apply that rule. And then we got a bunch of powers or exponent rules called the power rule. So we're just going to apply all of it. Everything except the logarithms and the base exponentials with a base, all right? These are the easiest of the rules. All right, 4 times 2 is 8, and subtract 1 from the power. There you go. Sometimes I like to start with this type of example, but today I decided to go a different route, right? Do all the hard stuff first, mainly because I wanted to make sure I got it in there. 3 times negative 4 is negative 12, and then subtract 1 from the power, x squared. 2 times 3 is 6, and subtract 1 from the power, so that's 1. Typically, we omit the ones. But if you want to put it, you can. Constant is 5. The derivative of x is just 1. And the derivative of the constant is 0. There you go. Bread and butter all day long, right? So that's almost the end. I want to show you a little bread and butter that needs to be constructed first. So this is sort of building your own bread and butter here. I also like to switch up variables a little bit. So I'm using y and t. Y and t. All right, so y is like f, and t is like x. So this is like bread and butter of a different, flavor here. Also, it's written out in factored form. So I want you to find y prime, or also known as dy dx. That's what I want you to find. Find the derivative dy d. Oh, not dy dx. Sorry, I almost forgot. Dy dt. The derivative of y with respect to t. So t is acting like x. It's going to play out a lot like example 7, but the variables are different. And I have to first get rid of the parentheses. So the first thing I'm going to do is multiply all of this times each one of these factors. Okay. I'll do the derivative in a second. So this is some sort of prep work. Got a lot of prep work before I could do the derivative. So I take the smaller expression, the one that only has 2 terms, and I distribute it into the larger one. If you choose, you can go the other way as well. It'll all work out the same. I go this way just out of habit. So then this becomes 3t to the 4th plus 4t squared plus 6t to the 3rd plus 4t minus 18t squared minus 24. I got to make one correction. 2 times 3 is 6, but that was correct. But 2 times 4 is 8. So just double check all your numbers. Make sure everything is correct. Simplify this. 3t to the 4th, then 6t to the 3rd, then negative 14t squared. Notice these guys combine. Get some combining there. And then plus 8t. Nobody combines with that. And then minus 24. So all of this is just prep work for finding the derivative. Now I'm ready to find my derivative here. I don't know if I can get that in there without having to erase because I'm already over time again. So now do the derivative. Back to bread and butter here. So you got 12t to the 3rd plus 18t squared minus 28t plus 8. See? 4 times 3 is 12, and then reduce the power. The power drops by 1. 3 times 6 is 18, and then drop the power by 1. 2 times negative 14 is negative 28, and then drop the power by 1. And then the last term becomes constant, so it becomes 8. And then the constant term becomes 0, and we typically don't write the 0. Okay, well, that was the introduction to the rules of differentiation, also known as the 7 derivative rules. There'll be more to come in the next part. We will get into some more exotic examples, and we'll get back to the business in business calculus. But until then, stay focused, do your homework, stay human. My name's Dr. Jordan, and I'll see you on the internet.